Now let's expand our understanding of stiffness method and stiffness matrix to find the stiffness matrix of a bar in tension. And the bar of our interest is something like this. A bar with two different cross-section areas, A1 and A2. What that means is that the two sections, if I call this section 2 and this one section 1, will not have the same stiffnesses. As a result, we'll have two elements, element 1 here and element 2 here, with K1 stiffness for element 1 and K2 stiffness for element 2. What's more, L1 and L2 could be different. As a result, again, the stiffnesses will not be the same, because if you remember, we said that for a bar like that, K is equal to E A over L, the stiffness. And if either of these, if Young's modulus, cross-section, or the length of these sections is different, that would mean that the two sections, or all the sections that we have in this bar, will have different stiffnesses. Let's assume that the force is applied to this end of it, and we consider a linear elastic model with Young's modulus of E and Poisson ratio of nu. Now we can discretize that element into two elements, or that bar into two elements, as I showed before. Here I have discretized into two elements, element 1, element 2, and three nodes. So I have node 1 here, node 2, and node 3. Element 1 has K1 and element 2 has K2 for this stiffness. And each of them will have their own free body diagrams. So F1x1, D1x1, again, the force of node 1 in x direction when attached to element 1 in the local coordinate system, and the displacement of node 1 in x direction for element 1 in local coordinate system. And the same is applied there too. So F2x1 and D2x1. And we have for node 3, which is at the other end of the bar, we have D3x2. And remember, that's because they're right now attached to element 2. And we have F2x2 and D2x2, which is different from here and here. So the second node, displacement and force in the x direction when attached to element 2, and the second node, force and displacement in x direction when attached to element 1, all in the local coordinate system. Next thing is to draw the free body diagram. So for node 1, I have the reaction force in this direction, and the nodal force, which is opposite to the one in here. So in the element free body diagrams, we draw them in the positive direction of the coordinate system, but in the nodal diagrams, we draw them in the negative direction. So F1x in the negative x direction. And here I have, for node 2, I have this force and this force. They're different in the element that they're attached to, but they're both the same direction, in the positive x direction. So here they will be in the negative x direction. So F2x1, which is the force for node 2 when attached to element 1, and F2x2, which is force for node 2 in x direction when attached to element 2. And for node 3, I only have one nodal force, which is F3x2, force of the node 3 in x direction when attached to element 2, and the force, which actually should be in the opposite direction. This is a typo here, or a mistake. I will correct it later. So that should be in the opposite direction because of this. So having known these, let's move on and apply the continuity and equilibrium conditions. So the beam that we have, or the bar that we have, is something like this. And node 2 is in here. And node 2 has displacements when attached to element 1 and element 2. One thing to remember, or one thing that is logical and reasonable, is to know that the displacement of this node, whether attached to element 2 or attached to element 1, should be the same. Otherwise, the bar would snap from this location, and the continuity concept would be falsified. So that's how we write this equation or this equality, that d2x1, displacement of node 2 in x direction for element 1, is equal to d2x2, which is displacement of element 2 in x direction, or node 2 in x direction when attached to element 2, and we call that the global d2x, which is which we get rid of the hat sign and the element number. Because the node 1 and node 3 are not attached to any other elements besides element 1 and element 2 respectively, we can just say that d1x1 is equal to d1x and d3x2 is equal to d3x. When it comes to equilibrium, however, we cannot say that the force of node 2 in x direction attached to element 1 is equal to the force of node 2 in x direction attached to element 2. And that's because if you look at here, the two forces are in the same direction. And so we have to add them, and we have to call them one global force, F2x. So continuity says that the displacements are equal, but equilibrium says that the forces have to be applied or summed to give a global force. And again, because we don't have any other elements attached to node 1 besides element 1, and only element 2 is attached to force or node 3, we can write these equations. These are the simplest ones to consider. So F1x 1, or force at node 1 in x direction when attached to element 1, is equal to F1x, and force of node 3 in x direction when attached to element 2 is equal to F3x. So these are basically in the global coordinate system. Now, from before, we saw that F1x, or we saw this equation in the local coordinate systems. So if I have F1x hat 1, F2x1 hat is equal to k1 minus k1 minus k1 k1 times d1x1 d2x1. Again, these x1s are from here, so k1. And for the second one, we have k2, and the nodes are node 2 and node 3. So if I come here, I can write that this equation for element 2. So this is element 1. And this is for element 2. F2x2, F3x2, k2 minus k2 minus k2 k2, d2x2, d3x2 all have hats. And here we have d2x1 or F2x1 and d2x1, which is different from these ones. So we also know that, again, F2x is equal to F2x1 plus F2x2. So F2x1, let me change the color of the pen. F2x1 would be found from multiplying this row minus k1 by this vector. So minus k1 d1x1, which is this multiplied by that, plus k1 d2x1, which is this multiplied by this, plus now I have to multiply this row, the first row of the second stiffness matrix, with this column. So k2 d2x2 comes from multiplying this by that, minus k2 times d3x2 is there. Now if I arrange them and take into account that this is equal to d1x, these two are equal to d2x, and this is equal to d3x, I can rewrite F2x as this equation. And so knowing that, let's move on to the next slide. And here I see that from the two local equations that I had before, F1x1 hat, F2x1 hat is equal to this equation. And for the element 2, F2x2 and F3x2 is equal to this right-hand side. I have to add these together to get the total stiffness matrix. So F1x, so this is node 1, right? This is node 1. So right there. And here is node 2. And this row is for node 3. So for node 1, I only have F1x1. But for node 2, I had F2x1 and F2x2. So I add them together. And for node 3, I only have F3x2. So I write this 3-element vector for the forces of the nodes. And if I remember from the previous slide, for this row, this was equal to F2x, and this one was what I would have for the relationship between that F2x and the displacement or nodal displacements. So this, let me write something that would make it easier to understand. So D1x, D2x, D3x, and you can see that this is D1x, D2x, and D3x. Let me just write this down again here. D2x and D3x. I see that F1x, actually from here I can see that, is equal to K1 times D1x minus K1 times D2x. So K1 under D1x, D1x, minus K2 under D2x and D1x, because they're not the same nodes, but the same displacements. And F1 doesn't apply to node 3, so I can write 0 here. Let's move to the third row first, because it's also easy. That would be from this part of the matrix. Minus K2 times D2x plus K2 times D3x. So minus K2 times D2x plus K2 times D3x. Now F2x1 plus F2x2 is equal to this, minus K1 times D1x plus K1 times D2x1. So I can write them here. These parts come from there. And then let me just change the color of the ink to make it more efficient. Now the second part comes from here. So I put those two together. So here, this part comes from there, and this part comes from here. And as a result, I'll end up with this matrix notation. F1x, F2x, F3x is equal to K1 minus K1, 0, minus K1, K1 plus K2, minus K2, 0, minus K2, K2. Again, this is D1x, this is D2x, and this is D3x, and D1x and D2x and D3x are written there. So we found that equation. Now we can apply the boundary conditions. We have a reaction force at node 1, which we presume that we don't know. We know that there is no external force applied to node 2, so that's 0. And we know that at node 3, we have a force applied, which is F in the positive x direction. This one was the stiffness matrix for the bar, and these are the displacements. We know that at node 1, it's fixed, so displacement is 0. But we know the displacements at nodes 2 and node 3. So here I have a 3 by 3 matrix. And why is that? If I go back to my example here, I have 3 nodes, right? So 3 nodes and 1 degree of freedom per node. So what that means is that 3 times 1 is equal to 3. I'll have to have a 3 by 3 stiffness matrix, which I've got in here. And the other thing is that the stiffness matrix is symmetric. So it's symmetric and it's a square. Those are two important functions of a stiffness matrix in our examples. Now I have 3 equations and 3 unknowns. My unknowns are f1x, d2x, and d3x. And my knowns, I'm gonna show them with the green color, are 0, f, and 0. The only thing that I have to do is to solve for this problem, which is pretty easy. What I do is first I take these 2 lines. So I say k1 plus k2 times d2x minus k2 times d3x. So basically I'm taking this portion of the matrix, multiplying it by this portion of the displacement vector, saying that they're equal to these 2 values. So what I'm solving actually is a 2 by 2 matrix from the entire system of equations. I don't know d2x and d3x, but I know 0 and f, and k1 and k2 are properties of the system. And then I can also write this part, which is from the 3rd row, minus k2 times d2x coming from here, and plus k2 times d3x equals f. If I add these 2 together, I will end up with this equation. So this and that will cancel each other if I add them, and this part will cancel out with that part. So I will have k1 times d2x equals f. So d2x, displacement of node 2 in x direction, would be f over k1. Now if I put this in one of the equations, let's say put it in the second equation, I would have minus k2 times d2x, which is f over k1, plus k2 times d3x is equal to f, which gives me d3x. Now if I put back these d2x and d3x's in this equation, in this matrix equation, and now I can write f1x is equal to minus k1 times f times over k1, basically coming from here. F1x, let me change the color so I can actually explain this more efficiently. Let's go pick blue. Now f1x is equal to k1 times 0 minus k1 times d2x. So minus k1 is here, and d2x, we found it over there, is equal to f over k1, which means f is equal to, or f1x is equal to minus f, which is exactly what we expected. So if we had these properties, Young's modulus of 200 gigapascals, Poisson ratio of 0.3, A1 is 10 centimeters and A2 is 5 centimeters squared. L1 and L2, let's say they're equal to 1 meter, and F is 200 newtons. The first thing we want to do is to find the stiffness of each of the sections of the bar. So K is equal to EA over L. The first one would have this stiffness. You put the 200 gigapascals here. We put the cross-section area there, and L is 1 meter. And then we put we find the stiffness of the second element from here, 200 gigapascals. The cross-section is 5 centimeters squared, and the length is 1, and we get this stiffness for the second bar. So if you remember, we had K1 minus K1, here minus K1, K1 plus K2, minus K2, minus K2, K2. So if I take the 10 to the 8 out of the equation, or out of the matrix, I'll have 2, minus 2, minus 2. These are K1 and minus K1. And let me change the color again to red. This is now K1 plus K2. This is minus K2. This is minus K2. This is K2. I know this and that, but I don't know F1x. I know the displacement at node 1 is 0, but I don't know D2x and D3x. But if I solve it, I can say that D2x is equal to F over K1, which is equal to 10 to the minus 6 meters. And D3x was K1 plus K2 over K1 K2 times F becomes 3 times 10 to the minus 6 meters, and F would be minus 200 newtons. So I solved that numerically as well. Now, having found those, we can also write these equations. I know that F1x1, so this is in the local coordinate system, now is equal to F1x, right, from the equilibrium, so minus 200. But I don't know the nodal force in the node 2 when attached to element 1. But I know the stiffness matrix, a local stiffness matrix of element 1 is this. If you remember, K1 was 2 times 10 to the 8. And these are the displacements, d1x and d2x. And I could write the same thing for this element, so element 2 here. Now this is K2 minus K2 and minus K2, K2, and these are the displacements of K or nodes 2 and node 3. Now if I solve from this equation, let me change the color. So for F2x1, I would have to multiply this row by this vector, would be 2 times 10 to the 8 times 10 to the minus 6, because this one is 0, would be 200 newtons. And F2x2 is equal to 1, so this row, 1 times 10 to the minus 6 minus 1 times 3 times 10 to the minus 6 would be 1 minus 3 times 10 to the 8 times 10 to the minus 6 is equal to minus 200. So the forces are negative or opposite signs, which means that node 2 is in equilibrium.